recording this. I need to move that all the way. There we go. All right. So from yesterday, we got to when we did an area, we just had and I'm using K for the letter today. Yesterday the letter was I. Today was K. We'll eventually get to I, J, K. But I just wanted to I and K right now. So anyway, we basically found the area by doing little rectangles underneath the curve, right? Well, this time I want to go beyond just 4. I want to go, how do I get the exact area? Do we all agree that if I took my pen and I colored, maybe, if I put enough of these, I don't have enough control with this pen. But do you see how if I really wanted, I could color it? If I put in enough rectangles, I'm not putting enough in. There we go. That's a little better. Right? There we go. If I put in enough rectangles, would I color this in and get the exact area? What does that mean? How many rectangles is that? It's just an infinite number of rectangles, right? So in reality, you remember those integrals you learned to write? That's what they are. So to find the exact area, the actual area, it is equal to the limit as the number, okay, it's the number of rectangles. Well, we're just going to leave that. Number of rectangles goes to infinity, right? Do we agree? Does that mean our delta x is going to 0? Do you understand? If we have an infinitely small width, does that mean we have an infinite number of rectangles? And does that mean we're going to get an exact area? So we're going to take a limit again. But we're taking a limit of a summation. The number of rectangles we're adding up, our numbers are going to start, from the first rectangle to n of them. And it's going to be that f of xk. And then we're going to pick delta x's that are all the same. But even if I didn't, if they're all going to an infinitely small width, are they all going to the same? They're essentially all going to 0, right? They're going to infinitely small. So it's all the same delta x, right? Does everybody see that? That thing, it's an integral. That's what integral means. This means this. It is the integral from a to b of f of x dx. It is called a definite integral, and that's what this whole section is covered. That's what we've been leading up to. It's a definite integral. You can definitely do this. Are you going to do an antiderivative? Yes, but we evaluate at the two interval, the a and the b, and we'll get there eventually. Right now, we're just going to learn the notation, okay? But eventually, you're going to learn to write this whole limit in terms of a and b. You know how yesterday, from writing the summation notation for our 3 or 4 rectangles, we could figure out where we were starting, right? And if you can figure out where you're starting and what your delta x is, can you figure out where you're ending? So you could figure out a's and b's. So eventually we're going to write this notation because that k, this x of k, is that the same x of k we learned yesterday, where we're writing x in terms of starting at a and how many delta x's do we have to add to get to the next step? Only we're doing it an infinite number of times. So basically, from yesterday, remember what we did for x, it was equal to the start. If we're doing right hand, was it equal to the start plus k delta x? That thing right there? We're going to put that in for that. We're going to have a function, and from that we can figure out, from this, we're going to do this and do that, we can figure out that definite integral. We'll get there eventually, not today. Today, I'm just telling you that if you add up an infinite number of rectangles, you're going to get this definite integral. And you know how to do antiderivatives, so now you're going to learn to integrate them, which is, it's the first fundamental theorem of calculus. Do we do that? Okay, so basically what happens is, suppose we have, we're going to do one that we know the area for. Suppose I have a line that's coming down like this. And This happens